ऐसा अगर भगवत जी
So good morning to all. Good morning to all of you. Is my AV is okay? AV is okay. Let me then I will start the class. Okay, thank you, Saksham. So let us start the optimal system operation continuation, but it is module 4. Module 3 we have completed. Module 4. So I am going to start. So two numerical problems in the last class we have done it. That was the last topic. We have done it. So today onwards we will take the module 4, that is optimal system operation. It is a continuation, but the topic is optimal load flow solution. So we have studied about the load flow solution, isn't it? So that static load flow equations also we have seen it. Static load flow equations. So what are the static load flow equations which we have developed in Newton-Raphson method, in which we are developed in Newton-Raphson method or Gauss-Seidel? It is a common thing which we are developed it, isn't it? So that is your load flow solutions. We have seen it. Decoupled, fast decoupled methods, 4 methods we have studied. But in this model, we are going to study the optimal load flow solution. In addition to that one, we are going to study the combination of hydro as well as thermal. So hydro as well as thermal scheduling, we are going to study in this module. Okay, so first let us see this one before moving on to that one. Optimal load flow solution, module 4 we are starting today. So this optimal load flow means, so earlier load flow solution, we are going to control only the real power flow in order to minimize, that is previous module 3 we have seen, we were controlling only the real power flow in order to minimize the total operating cost or the total production cost. But in this optimal load flow solution, in addition to real power, so we are going to see the reactive power flow solution also. So here it is a optimal load flow means it is a general form, more general problem in which we are going to assess the real and reactive power flow so as to minimize the instantaneous operating cost. That is instantaneous operating cost. You have seen that one, CI, cost equation. What is the unit of cost equation? Is rupees per hour. And what is the unit of your incremental fuel cost? It is rupees per megawatt hour. So this is what we have seen it. So in this optimal load flow solution, both real and reactive power flow solution we are going to study so as to minimize the instantaneous operating cost. That is the objective in this one. So that means it is a static optimization problem with a scalar objective function. The same scalar objective function which we have seen it in the earlier case, that we are going to consider. So which is a static optimization problem. So with this brief introduction, let us see optimal power flow without inequality constraints. So you have seen that one optimization problem in power system. Optimization is a tool which is used to solve the various numerical problems. Understood? Either it may be in power system or civil engineering or electronics engineering or anybody, even business management people, they can use it, these optimization tools. So in the power system, so we are using the power flow equations to get the optimal solutions. So that's why it is optimal power flow without inequality constraints. So constraints will be there. You have a equality constraints and inequality constraints. What are the inequality constraints? We have seen in NR method, isn't it? So that may be greater than or equal to constraint or less than or equal to constraints. These are your inequality constraints. So what is equality constraints? Is your power balance equation is equal to 0. That's what we have studied in load flow equations. Now here we are going to study both your economic operation as well as your load flow. Combination of these two we are going to study in this module. Module 3, purely we have seen economic dispatch without considering any of our load flow solution. In this module 4, we are going to consider the economics dispatch or economic scheduling in addition to our load flow solution, because in order to assess the cost of generation or the production cost, you need to have the load flow solution. Clear? So with the combination of load flow and economic dispatch, we are going to study in this model, that is optimal load flow solution. Under this one, optimal power flow with inequality constraint. So without inequality constraints, let us take first case. Then we will implement the inequality constraint. Then we will see what is optimal power flow. So what is optimal power flow actually is a power flow problem, that is load flow problem. Actually to say optimal power flow means it is a load flow problem. Only the difference is in this optimal power flow, a certain controllable variables are minimized, so are adjusted to minimize the objective function. Please remember the objective function is to minimize your total operating cost. That is your objective function. Like module 3 what we have studied, that is objective function. The same thing we are taking it here. Clear? So optimal power flow is a power flow problem or a load flow problem in which a certain controllable variables are adjusted to minimize an objective function. Understood? So what are the control variables? Usually you can control your generation by changing the excitation or by opening the steam valve in thermal power plants, isn't it? So you can control PGI. This is one of the control variable. What are the other control variable? Your transformer tap settings. We have seen that one also, isn't it? Transformer tap settings can be varied. Transformers tap settings can be varied, and voltages you can vary. Voltages at buses you can vary, etc. These are some of the controllable variables. By adjusting these controllable variables, you can minimize your objective function. Your objective function here is to minimize your operating cost. So that you should remember. Please keep it in mind. In this module, we are studying both economic dispatch in association with your load flow solution. So you should need that load flow solution. You need the equations, power flow equations, which you are derived it. So let us take it step by step here. Now objective function is to minimize the operating cost. This equation, nothing new here. Already we have taken it here. This equation, isn't it? That is total production cost C is equal to CI of PG. That means it is what is the cost of generating PGI. This CI of PGI is nothing but cost of generating PG at ith unit. I is varied from 1 to NG or N, number of generators, number of generating units. This is your objective function, nothing new here. The same objective function we have considered in the previous module also. Understood? Now, once you have considered the objective function, then what you have to do, so now you see this is your economic dispatch. Minimize this cost. Now, as I said, we have to include both the things, load flow. Now, for this one, in order to minimize this one, we need to have these two equations. What are the power flow equations? Can anyone tell how many power flow equations? How many power flow equations you have to evaluate it for a PQ bus? How many power flow equations you have to evaluate it for PV bus? Can anyone tell? Actually, module 2, I have told this one several times, and you people, of course, you have answered. Now, module 4, just I want to check whether you are having idea about this one or not. How many power flow equations we have to solve it for PQ buses? How many equations? And how many power flow equations we have to solve for PV buses? We have developed two basic power flow equations. Basic power flow equations based on that one. So let me see whether you can remember or not. Load bus 2, generator bus only 1. That is the answer given by Sushumna. So fine. So please, to refresh your mind, once again I am telling you, for load buses, that is PQ bus, load buses are nothing but your PQ buses, two equations, power flow equations you have to evaluate. What are those two equations you are going to evaluate? Real power flow and reactive power flow. Real power flow and reactive power flow equation you have to evaluate it. And at PV bus or generator bus, you have to evaluate only one equation, that is real power equation. Real power equation you have to evaluate. Please keep it in this one in your mind. Again, I am repeating it. For load or PQ buses, two power flow equations has to be evaluated. That is, one is for real power, the other one is for reactive power. If it is a PV bus or generator bus, only one power flow equation has to be evaluated. That is real power flow equation you have to evaluate. So here, this method we will be considering under NR method, Newton-Raphson method. We will be implementing it here in this economic dispatch. So you should have that knowledge, NR method knowledge here. So let us take here. Now objective function we have defined. So for each PQ bus, this is the real power flow equation. This is the real power flow equation, isn't it? Please recall this one. If you are having load flow notes, you can check it out. Pi is equal to this equation you have. Pi is equal to this equation you are having it. This is the real power flow equations which we have developed. How we have developed, how we have obtained, already I have explained this one in module 2, clear steps, isn't it? So when I am taking this RHS quantity onto LHS side, so Pi minus of this whole thing is equal to 0. Call that as equation 1. Call that as equation 1. Is it clear? Now for PQ bus, another equation also we have to get it. What is that another equation? Qi is equal to minus of this equation with sign component, isn't it? Qi is equal to minus of this component with sign component. So minus is there. So when I am taking that one onto LHS side and equating to 0, this will be your resultant equation. I am taking, so minus is there, so it will become plus of this same equation with sign component. Understood? So this is your second equation. These two equations we have developed in load flow solution under NR method. Only the thing is, there we have written Pi is equal to this equation, Qi is equal to minus of this equation. But what here we are doing it, we are taking that one to LHS side and equating to 0. That's what we are doing it here. Call that as equation and 1, 2. So for each PQ bus, evaluate Pi, these two equations. Evaluate these two equations. Then for PV bus, only one equation has to be evaluated. That means this equation has to be evaluated. That is real power equation. But here real power flow minus of this one whole thing equal to 0. Clear? Hope you understood this one. Equation 1 and 3 is same. There is no difference. Only thing is, for PV bus, you have to evaluate this equation. Understood? Equation 1 and 3 are same. So, is there anything new thing is here? Nothing new. So, already you have studied these equations. We have derived this one in load flow solutions. Only thing is, we are equating those equations, power flow equations to 0. And for PQ, these two, for PV bus, this alone you have to evaluate it. Okay. Now, it is to be noted that at ith bus, power system means what? You will have several number of buses. So, at ith bus, what is the injected power at ith bus? What is the power injected at ith bus is generation minus the demand, load demand. This is a general formula which we have studied, isn't it? Generation minus load is your injected power at a particular bus. If you want to identify anything, so you have to find out what is the injected power at that bus and what is the load. So therefore, power injected at ith bus is equal to PGI minus PDI. This is your real power injected. As I said, optimal power flow means we have to take care of both real and reactive power. Then what is the reactive power injected at bus I? Is your QGI minus QDI. Hope you understood this one. So at ith bus, what is the real power injected and what is the reactive power injected is equal to generation minus load at that particular bus. Suppose if you are taking what is the real power injected at bus 2, P2, this becomes PG2 minus PD2. Clear? Now this is what we have written, and obviously PGI, PDR are your load demands at bus I or at ith bus. Now all these equations 1, 2, 3 can be represented in vector form. Understood? These equations 1, 2, 3 can be represented in vector form. How it is represented in vector form? Please remember these three equations 1, 2, 3. Equations 1, 2, 3. I will be representing these three equations in vector form. Okay. So that I will be showing it here. Now how to represent? Now let us represent f is a function of variables x comma y. How it is represented by equations 1, 2, 3 in vector form. So first you define a function which is a f which is a function of x and y variables. What is x? Is a state variable. X is a state variable, also called as dependent variable. Dependent variable. Y is called as controlled variable. Controlled variable. Of course, complete y is not a controlled variables. A part of y is controllable. Understood? So x is a state variable, also called as dependent variable. Y is your controllable variable, which is called as independent variable, which is also called as independent variable. So define a function of state variable as well as controllable variable is equal to, it is represented in a vector form, equation 1, equation 2 for each PQ bus. If it is a PQ bus, two equations will be there, 1 and 2. If it is a PV bus, equation 3 alone, you have to evaluate it. You have to solve it. Hope you understood this one, this point. Understood? So define f of xy is equal to equation 1, 2, 3 in vector form. Equation 1, 2 for each PQ bus, equation 3 only for PV bus, you have to represent it. Now where x is a state variable, also called as dependent variable, and is given by x. What are the what is state variables? I think you might have studied in control system, state space representation of any control system. What is state variables? Are the smallest set of variables which determines the complete behavior of the system. Understood? What is state variable? Is the smallest set of variables which determines the complete behavior of the system. So that is your state variable. So here x is a state variable, also called as dependent variable. Why it is called dependent variable? Because these are dependent on some other parameters. X is equal to, for PQ buses, you have to evaluate magnitude of Vi and delta I. For PQ buses, understood? So you have to evaluate both the magnitude of Vi and delta I, isn't it? At PQ buses, P is known, Q is known. What is unknown? Vi and delta I. Those two things you represent it in vector form. Then for each PV bus, what you have to evaluate? Delta I, isn't it? So you have to evaluate delta I. Okay, so this is only delta I angle, you have to take it. So it is dependent variable. Understood? Q is not a dependent variable here. Understood? So this is what the variables, three variables we are having it. X is nothing but state variables. Now what is Y? Is called as controllable variable, are also called as independent variables. That means which are independent, is equal to, now in the, while representing the control variables, you have to include the slack bus also. You have to include the slack bus also. Understood? While representing the controllable variables, you have to represent the slack also. So for slack bus power, for slack bus, sorry, this is Y. You correct this one, this is Y. Y is equal to, only I will correct it. Okay. Y is equal to, for slack bus, for only one. Slack bus is always only one slack bus will be there. This is what I said it. So it will be V1 delta 1. V1 delta 1. Understood? Magnitude of V1 delta 1. Then for each PQ bus, for PQ bus, so P and Q are known. So Pi is known, Qi is known. For each PV bus, P is known, V is known. So P is known, V is known. So the known values are your controllable variables. Understood? The known values are your controllable variables, that is independent variables, are nothing but your independent variables. Is it clear? Now how to represent the state variables? How to represent the control variables? Why? While representing the control variables, you have to include the slack bus variables also. So at a slack bus, we are interested in magnitude of voltage and the magnitude of, and the phase angle of the voltage delta 1. At PQ bus, so Pi, Qi. Then for PV bus, Pi and Vi are your variables. Is it clear? Now is it clear for you? What is X state variables of your power system? If it is a PQ bus, it is voltage, magnitude and angles. If it is a PV bus, it is only phase angle, voltage, phase angle. You have to consider. Those are state variables. If it is a control variables, then it is almost you will have this type. For slack bus also you have to include PQ bus, Pi, Qi, PV bus, Pi and Vi. Okay. So please keep it in mind what are controllable and what are state variables. Now after this one, once again, this I am going to partition into two vectors, two parameters, U and P. So in this one, U is controllable, a part of U. See, I said even the Y is controllable variables, the complete Y vector is not controllable. A part of Y is controllable. Understood? So in order to justify that statement, this Y is also represented as U and P, where U is your controllable variable, where P is your uncontrollable variable. That means remains constant. Understood? Remains constant. P is your constant. This is your controllable variable. You see, Y is consisting of UP, submatrices U and P, out of which U is controllable variable. Because some portion is controllable variable, that's why Y is called as controllable variable. Whereas P, submatrix P, is uncontrollable variable. Understood? So this is how we are going to derive it. So the objective function include, in the above formulation, the objective function must include the slack bus power. Understood? Why we have to include slack bus power? Suppose if we are not including slack bus power, what happens? What is the slack bus function? Any additional power is required that will be supplied by the slack bus, isn't it? Suppose if you are not considering the slack bus power, you are considering, your objective is to minimize the total operating cost. That means even slack bus cost also, because slack bus also uses the fuel to generate the power. So that slack bus cost also you should consider when you are considering the objective function to minimize the total operating cost, isn't it? So if you are not considering, then the maximum power generation will be allocated to the slack bus. Then your objective function, you are not going to fulfill it, because if you are excluding the slack bus power. From where the slack bus will generate the power? It also uses the fuel to generate the power. So therefore, you have to include the slack bus power in order to satisfy your objective function. Is it clear? So that is the important thing, you should remember it. The vector of independent variables, Y is independent variables, again partitioned into two parts, U and P. That's what I have shown it, isn't it? So in this one, a vector U of control variables which are to be varied to achieve the optimum value of the objective function. This is what I said it. Y is again partitioned into two submatrices. One submatrix is U, which is controllable variables. These controllable variables can be varied to achieve your objective function, to minimize your objective function. So what are the control variables? Example, I told PGI generation. You can control by changing the excitation or by opening the steam valve, etc. Or you can control the voltages at the buses. How to control the voltages at the buses? You can use a capacitor bank or inductor bank at the buses in order to vary the respective reactive power. If you vary the respective reactive power, the voltages at that particular buses will also vary. This is that old method, that is traditional method. Then what is the modernized methods of controlling voltages at the buses? Is using your FACTS controllers. Again, I am repeating it. FACTS, FACTS controllables. That is flexible AC transmission system controllers. Flexible AC transmission system controllers. These are power electronic based controllers. These are power electronic based controllers which are used in our power system to control the power flow. Clear? Now U is a control variable. Then what is P vector? It is a fixed, or it is a disturbance, or it is uncontrollable parameter. This is what I have explained it, isn't it? U is a controllable variable. P you cannot control. It is fixed because of disturbance, or it is an uncontrollable parameter. Understood? So that is, this is U and P I have represented here. U is controllable variable. This may be PGI or voltages at the buses or tap settings of the transformers. All these variables will be coming under U. And P is fixed, which cannot be controlled. But still, we call Y is a controllable variable because some portion of control Y is controllable. Control parameters may be voltage magnitudes on PV buses, that's what I said, or PG8 buses with controllable power, or transformer tab settings, etc. This is what I said it. Now the optimization problem which we have defined earlier, now we are going to rewrite it. The optimization problem which we have defined, we are going to rewrite, and we are going to see how to solve this optimization problem. Clear? So how to rewrite this problem and how to solve by using some iterative methods, we are going to study this one in the next class. Understood? Because I lost some time in today's class, so I could not complete this one. Anyway, I will continue from this point onwards in tomorrow's class. So till this point, I hope you don't have any doubts. So in the module 4, just I started. So I given the brief introduction about a optimal power flow problem. Again, with these assumptions, so with these controllable, uncontrollable variables, we are going to redefine the optimization problem, which we have already discussed in our module 3. Clear? Okay, that we will see it in the next class, how we are going to redefine or restate. Any doubts? Anyway, nothing has been covered in today's class. Hope you people will not have any doubts. Okay, I think you have next class, I think. Okay, thank you one and all. Take care, bye.